All right, today we're looking at lesson 45. We're looking at projectile motion and then the motion of center of mass. So hopefully you'll understand projectile motion and the motion of center of mass after this lesson. Projectile motion problems consider the motion of objects that are in free fall. These objects have a velocity component in the vertical direction and they have a velocity component in the horizontal direction. Projectile motion problems take something. We have a building and you've got a person on top of it and they throw it off and then it falls. But it doesn't really do that exactly. It has a continuously curving shape. We have looked at falling body where they just go straight down, not where they actually curved out. Okay, so that's what's a little bit different here compared to the just falling bodies problems. So projectile problems are very easy to analyze if we make these three assumptions. The effective air resistance is negligible. Just like on everything, we are basically neglecting all air resistance. The vertical acceleration due to gravity is constant everywhere along the path. So your acceleration due to gravity is the same the whole time. The rotation of the Earth does not affect the trajectory. Now, I realize that technically you do have air resistance. Your acceleration due to gravity may change, and the rotation of the Earth can affect the trajectory of some problems. But we are assuming that those do not happen, and it's to help make the problem simpler and easier for us to understand and to practice so that we understand how it works, even though if we did it in real life, we wouldn't get the exact same thing. So the vertical motion is exactly like the vertical motion of a freely falling body that has an initial upward velocity of v sub 0 sine theta sub 0 and is accelerated downward at a constant rate of 9.81 meters per second per second. And so you have a projectile motion problem that's basically going to be two problems in one. One of the problems is going to be about an object whose horizontal velocity does not change. The motion and the position equations for this body do not have the acceleration components. So this is what your x motion equations will look like and your x position equation. You do not have the plus a sub x t, and you also do not have the 1/2 a sub x t squared. So both of those terms are gone. The other problem, so this is about one where the horizontal velocity doesn't change. The other one is whenever it's a body falling freely in space, a freely falling body that's in space. And so for your y motion and position equations, you have, just like you normally did, velocity plus acceleration times time, and then position plus the initial position plus the velocity times time, plus 1/2 acceleration times time squared. And so it says that the trick to solving most of these problems is to use the y equations to find the time. So most of the time we're going to start with these two equations on the board to find our time, and then we're going to use that time in the x position to figure out what distance it traveled. So let's look at an example. A projectile is launched horizontally from a tower that is 40 meters tall. The initial velocity is 60 meters per second. At what distance from the tower will it impact the ground? Okay, so we're going to start with our y equations. We have v sub y equals the initial velocity, and then we also have the position equation where y equals y sub 0 plus v y 0 t, and then plus 1/2 a sub y t squared. Honestly, I think half of the issue with these problems is all of the subscripts. You're not used to quite so many subscripts on your equations. But that's really, it's the same kind of equation that we've already been dealing with. It just now has all of these subscripts. On these, the initial velocity in the y direction is 0 because we've got a projectile and it is thrown horizontally. And so it goes this direction only. That's in the x direction. In the y direction, there is no velocity. So that term goes away and this term goes away. And so now we want to know when will it hit the ground. And so that's when our y is equal to 0. It initially was 40 meters up in the air. So it started at 40 here and then it ended at 0 somewhere down here. And it's going to start off and then it's going to fall down here to 0 meters. So it started at 40 meters and ended at 0 meters. And then we have plus 1/2. The acceleration is negative 9.81. And then we have t squared. And so if you solve that equation for t, you should get 2.856 seconds. And so now we can actually use that in our x equations. Notice that we didn't actually use this equation anywhere. So we didn't actually use that equation on the left. We didn't need it. You may need it in some problems, you may not. Now we're going to go to our x position equation. So I'm going to write it. We have x equals x sub o plus v sub x o and then times t. We know that our initial x position is 0. I'm going to draw a picture on a coordinate plane for you. So our object starts here at 40 and it's going to fall somewhere over here. And this is what we're actually looking for, the distance here. We want to know what is that point when our y is 0. And so our x, it's on the y-axis, so our x original position is actually a 0. Okay? Because we're starting from the building and we want to know how far it went away. And then we have a velocity initially in the x direction is 60 meters per second because it's launched horizontally. All of the velocity is horizontal. So we have 60, and then we plug in the time that we found over here. So we have 2.856. Use the whole number that's in your calculator, and you should get 171.4 meters. But we only have 3 sig figs in our answer, so it's going to be 171 meters. Okay, so that would be how you would work that example. Looking at the next part, we've got the, here we go. We've got another example. A projectile is launched at an angle of 40 degrees above the horizontal with an initial velocity of 200 meters per second. How far from the launch point will the projectile strike the ground? And so what we actually need to do on this one, since it's not horizontally launched, we have both a horizontal and a vertical velocity. And so we have our projectile here. And so it went this direction. And so we can draw a triangle here, and we can find our velocity in the x direction and our velocity in the y direction initially. And so this angle is a 40-degree angle, and the initial velocity is 200. And so if you use sine and cosine, your v sub y initially is going to be 128.6, And your v sub x initially is going to be 153.2. So now we're going to use our x and y equations for motion and position, and we want to substitute into them what we can. So we know for our y motion, we have v sub y equals v sub y 0 plus a sub yt. And we found this number to be 128.6, and the acceleration is negative 9.81. So we have 128.6 and then minus 9.81 t. Okay, and then for our y position equation, we would have y equals y sub 0 plus v sub y 0 t plus 1/2 a sub y t squared. Our initial y value is 0 because it was launched at an angle of 40 degrees above the horizontal with an initial velocity of 200 meters per second. It doesn't tell us anything about how high it is off the ground. So our initial height is 0. Our v sub y o we found. It's the 128.6. And then we have t. And then plus 1/2 times negative 9.81 is going to be negative 4.04. I just completely lost what that number, 905. That's what it's going to be, 4.905 and then t squared. Okay, so those are the y parts. Now we want to do the y value here. It wants to know how far it will strike the ground. So when is the final y value? It's also going to be 0 because it started at the ground and then it ended at the ground. So we can use this and we can solve for a t. So I can actually just take out a t, like divide by t, because at time of 0 it hit the ground, and then again it's going to hit the ground because it's a parabola. And so this is at time 0, and then this is going to be another one. It's technically a quadratic, but one of them is going to give us a 0, and then the one that we actually want to know is this one right here. So you can go ahead and divide by t. Normally you don't want to divide by variable, but you can do that. And so when you solve for your t, you should get 26.22, and it's going to be seconds. So that's your time. Now we want to use our x motion and position equations. So we're going to start with the x position because it asks about how far from the launch point will it strike the ground. That's talking about a position. So x is going to equal x sub o plus v sub xo times t. So our initially our x position was 0 because it started at the ground. We are assuming that this point here is basically like the origin. We found our v sub xo to be 153.2, and then we solved for the t just a second ago. It was 26.22. So if you plug that in, you're going to get 4016.9, and if you use your sig figs, 4020, no bar over the 0, and then m for meters. Okay, so that's how you would deal with the projectile motion ones. Again, it's basically two problems. One of them is dealing with the x values, and one of them is dealing with the y values. You usually want to start with the y values to find your time, and then plug that into your x values, your y equations to find your time, and then plug those into your x equations. Okay, so looking at the motion of center of mass. In our discussion of projectile motion, we did not consider the shape or the mass of the projectile, and we did not consider the possible ramifications of the rotation of the projectile. A mathematical investigation of a combination of translation motion and rotational motion is quite complex and is above the level of difficulty of a beginning physics book, which this is a beginning physics book. So the mathematical investigation of translations and rotations in motion is apparently too complex for and above the level of what we are learning this year. So you should be thankful about that. We're not actually going to deal too much with it. It can be shown, however, that a mass will rotate about its center of mass, and the path of the center of mass is going to be identical to the path of a point mass. And so they show you a picture, actually they show you a couple of pictures in the book to help you kind of see what they look like if you want to look on page 304. But the center of mass is going to move just like a particle would that has all of the masses at that one point. And so if you want to look, they've got a hammer, and then they've got a swimmer, and you can kind of see the pictures there. But it's going to keep the same shape as just a point mass. And so we're not going to worry about the translation motion and the rotational motion for this particular physics book. So your homework is 1 through 20, so you need to make sure that you do that tonight so that we can go over any questions that you have tomorrow. And then also look at the curveball questions 1 through 5.